Hello everyone. In this video we're going to continue talking about convolutional neural networks from last time, but we're going to talk about making the results better. Remember last time when we worked on the CFAR data set, the results were not like bad, but they were not impressive, especially for a couple of classes, the dogs and the cats, which is a little bit inherently due to the low quality of the images, and they were not really distinguished so much from each other. But there are some steps we can do to enhance the result a little bit. One of them is data augmentation, and that's not just for this case. That's used in anywhere that you can basically work with images. Okay, because when you have other forms of data and you perform machine learning on them, deep learning, anything, it's not easy to augment the data. It's not easy to add more to the data. Okay, so if I have a bunch of grades in my class, it's not easy to add more grades unless I'm really forging data, which does not mean I get any honest results. But if I have this image of myself, this is the original image, and the goal is to detect this face or some features in it, well, one of the things I can do is to do translation, right? I can translate it up, down, left, and right. And basically, from this original image, I get a bunch of shifted, translated versions, or I can rotate it like this. I can also scale it down or up, or I can flip the image. We see here is flipped with respect to a vertical edge, or I can do flip with respect to the horizontal edge or something. Or I can do shear, right? If I do shear, then the image will go something like this, and then in one direction the features will be stretched, in the other direction might or might not. So there are lots of things. Or I can make the pictures a little bit darker or brighter. I can improve the contrast. There are so many things you can do to create a lot of data from the original one. And the good thing with these is you have more data, and you know deep learning is always hungry for more data. You give it more data, you have a better chance of basically finding those features in a more robust manner. Because now if you can detect the feature here or here, it means it's kind of shift invariant or translation invariant. If you do it with these guys, you might do scale or in rotation invariant, right? You might have invariance with respect to flipping and so many things with respect to brightness. So they make the method more robust, okay? And again, that's a capability that you have only with images. With many other types of data, you cannot do that. But in TensorFlow and for CNN networks, you can do that. How? Let me show you that. So here, there is this method called tf-keras preprocessing.image. So it's a portion of under the preprocessing for images, and it's called image data generator. What does this do? Well, it allows you to do a range of different transformations on the image. Like what? Like feature-wise center. What does it mean? It means to make the average of any feature set it to 0. Or STD normalization, right? That means make a feature in the image, make the standard deviation of that to 1. You might do a whitening on the image, or called ZCA. You might rotate the image in a range. So you provide a range, and then here when you say 0, that means don't rotate it. But if you say 90 degrees, right, and then it can rotate it from 0 to 90 degrees in a range of angles, right? Or width shift or height shift. Here you provide a number between 0 to 1, which is a percentage of the width or height of the image. If you say 0.1, means I want this feature to be shifted left and right by 10% of the image width, or 10% of the image height go up and down. I want the brightness range to change. I want to apply some shear. I want to apply some zoom. I want to fill some features. If there are holes in them, I can use the nearest method, right? There is horizontal Philip, vertical Philip, and some of them are either true or false, whether you want to apply them or not. Some of them are a range, okay? But you see, there are lots of different things that you can do. You can rescale, right? You can do brightness, shift brightness range. There are lots of things you can do, and you can artificially add more data. Now you might say, would you do this before you start training the network, or do you do it during the training? Well, if I do it ahead of time, this is not for ahead of time. This is for real-time data augmentation. So you might say, why don't you do it ahead of time? So you have this image, go ahead and ahead of time apply a bunch of transformations, get all of these extra images, and then bring them into TensorFlow and start training the network. Well, the problem is this. The problem is these images, if I have, like in this case, 60,000 of them, and I only get what? A few extra transformations. It's a translation, a rotation, right, or two translations in this case, a Philip, and so on, then that means I'm basically making the size of my data 4, 5, 10 times more. And those many images, you might not get enough of room, enough of memory in TensorFlow. It most probably will not even give you that much of room and memory to upload all of these huge data sets, okay, that you have. The original one plus all sorts of these augmented ones. So TensorFlow rather create those images on the go during the training, creates those and pass them with batches, batch, pass them to the network and train them in real time. Yes, it takes more time to train the network, but it is not going to demand a ton of free memory from the TensorFlow. Okay? So this is called image data generator. Now, how would you exactly use it? Let me show you. So here we are working on the CFAR 10 data again. We do the exact same thing as last time. We bring them in, we get rid of the extra dimensions, we add the dimensions we need, we convert them to double between 0 to 1, everything, the number of classes still 10. Now, you see here, I'm basically doing the same thing as last time, right? Except this time I'm using that format that is convolution and max pooling, right? Instead of the stride. And there is one extra thing I'm doing here, batch normalization, which I explained. That's a second method that we do to improve the results. But basically, you see it's the same conv 2D and max pooling, conv 2D and max pooling, the same number of values. I added a little bit more to my dropout in one layer and reduced it in another one. I'm trying to avoid overfitting that we saw last time. The same optimizer, the same loss, the same metric. Everything is the same. Now here, what is the difference? Look. Here, I use this pre-processing image generator. I pass to it everything that I want changed. And here, all I want is 10% change up to, from 0 up to 10% translation in the X direction, up to 10% translation in the Y direction, and some horizontal Philip. Okay, true. So only those, nothing else. And with this, I create this object data generator, and then this data generator has a method called flow, which you pass to it your X train and Y train and a batch size. So each time it will apply all of this to this X train and Y train. So now it gets a huge amount of images, right? Let's say if it does it on all of these images, you might get, instead of 60,000, you might get more than 240,000 images or so. But it's not going to feed all of them at once to the network. It is doing it batch by batch. What is the size of the batch? How many images would you pass? You determine that. It's a hyperparameter. So here I say pass every 32 images at once and train. So this data flow is doing that, this data generator flow. It takes this X train, Y train, and batch size, and it will create this train generator, which creates the train of the train set of X train and Y train in batches. So when you do the model fit, these X trains and Y trains are coming in batches. Okay. The validation data set is still the same. Now the epochs, I use 40 epochs. One extra thing you have to add, and that is called steps per epoch. Okay, so here one epoch means going through all of the images. So how many times, how many batches do I need to pass in so I go through all the images? I need to find the size of my X train, the new one, which has all of these extra augmentations to it, divided by the batch size. Make sure you get an integer number using this double backslash, right? Double forward slash. So now the result is an integer number, and then pass that number to steps per epoch. Okay, so let's say if I have what? Let's say in this case I have 240,000 images, right? And the batch size is 32. That means per epoch I need to feed 7,500 batches to the network. Okay, so each epoch involves passing 7,500 batches to the network. Then you go to the next epoch. And so here these epochs are going to take you a lot more time. Okay, because you're generating data in real time and doing it in batches. And the batch part is good because it doesn't do the update per image, it does it per 32 images. But since you have a lot more images, this thing is going to take you a little bit more time than the code that I had last time. But if you go down here, the good thing is you can see that the accuracy here goes to 0.82 and on the training to 0.96. And if you plot the accuracy, you see that they are still going up, although this one is kind of plateaued right now. It's kind of flattened, so it's not getting much better if you go more epochs. And that's again because of the inherent low quality of the images. But it's much better than last time. And if you look at the confusion matrix, remember this time? Last time, one of them was 200 and this guy was 400. Now you see this guy is 600 and that guy is 100. Okay, so I'm doing better this time compared to last time. And that is one reason is because of this augmentation, real-time augmentation, but the other reason is the second method I used here for improving my results, and that is this guy called batch normalization. So what is batch normalization? Let's talk about that one. So batch normalization is another operation or a layer that we have. So basically it normalizes the batches, and normalization, you know, it means what? It means subtracting the data, the average of the data from the data, and dividing by the standard what? Deviation. So now the average of the data is 0 and the standard deviation is 1. And the thing we do is we don't only do it on the results from the initial convolution. Every time the data comes out of a convolution layer, we make sure we normalize it. Because even if these images that we are passing in, are already normalized, when they come out of this first convolution layer, they're not going to be normalized again. So here with these batch normalization layers, we force them to go to what? Mean of 0 and standard deviation of 1, which most of the time the neural networks prefer. Okay, so now, because we are doing it in batches, that provides something. That provides some help. What is that? Well, since we are doing it in batches, every batch is a little bit different than the other batches. So, basically, with these variations that you have in different batches, you're making sure that your system is trying to avoid overfitting, but being less sensitive to all these small variations from one batch to another, from 1 mu x of one batch and 1 sigma x on one batch to the mu and sigma of the other batch. And instead of trying to fit all those small variations in these training images, it tries to fit to the bigger pictures so it can avoid overfitting. And we also use dropping layer to help us. Okay, so here with this batch mechanism and with the drop layer, we are helping as much as we can to avoid overfitting. Still, we can, especially if we use a ton of these filters and a ton of these weights and a ton of layers, we have a good chance of what? Overfitting. Okay, so we have to here play with different hyperparameters and find the best set for this set of data. But in general, these are two mechanisms that we do here, the batching and drop up, to avoid overfitting. And as I said, the batch normalization also passes data with mu of 0 and standard deviation of 1 to these convolution layers, which they most of the time prefers. Now, they do another extra thing. Sometimes these convolution layers might not really actually prefer a mu of 0 and a standard deviation of 1. They might prefer what? A mu other than 0 and a standard deviation other than 1. Okay, but maybe not the original mu and sigma, a new one. Well, how do we know which mu and which sigma they like? We don't. So what does this batch normalization layer do? First, it brings the data to mu of 0 and sigma of 1, then it applies a linear transformation on them with two parameters a and b. And this a and b are unknown parameters, okay? They determine the mu and sigma of the new data, okay? And here the new average is going to be b, right? You clearly can see that, and the new standard deviation probably a, but they don't then when it starts with random numbers for a and b, and then adds these a and b to the unknowns of the problem, and using a steepest descent or any other optimization algorithm, here Adam, it tries to learn what a and b are good, what linear transformation is good. Okay, so if I want to write them for you, it brings them from mu and sigma to what? To probably b and a. What b and a? It tries to find which one are good, okay? So it does two things at the same time, and that's why these batch normalizations are good layers to add. The only important thing you have to pay attention, you only add them after a convolution layer. You don't add these batch normalizations after a dense layer, okay? So you are not going to do that, okay? And that's what you see I have done here. I have added them right after convolution and right before pooling. Right before pooling, and then finally I have applied my training, and you see my accuracy both on the training set and on the test set are quite a bit better than what it was last time. Again, there is no way I can make them like perfect in this case. The training data set has too much variations, too much noise, too much pixelations, and low quality, but I could definitely improve the results, although I have not added any more layers or neurons or anything. Just with 2 extra steps, I made the results better. So hopefully this video was useful to you. Again, I give you the download link for this one so you can play with it and learn from it, and I'll see you in the next video. Thank you.